Good evening and welcome to the first Ask a Physicist webinar of the new year and the new semester. Before we get started, I have a few announcements to make. First, we are very excited to announce that Paul Nurse, Nobel laureate and director of the Crick Institute, will be giving our Beyond annual lecture on March 24th. The title is What is Life? And it will be held via Zoom at 1 p.m. Mountain Standard Time. So mark your calendars and be on the lookout for more information to come next week. Secondly, I would like to remind everyone of our next Ask a Physicist on February 22nd at 6 p.m. The topic is dark energy, so also be on the lookout for those registration links, which are also coming soon. For tonight's event, we have Paul Davies and Sara Walker answering the question, did life on Earth happen more than once? And I'd like to remind everyone that you can ask your questions via the chat feature within Zoom. Our moderator for the evening is Maulik Parikh, so I will go ahead and pass it on to Maulik.
Thank you, Jessica. Welcome everybody to the Ask a Physicist webinar. And we have this is the first of a series of 4 events that we're going to have this term. We had a similar series last semester. So the way it works, as you probably know, is that there's a topic. We're going to have brief presentations from our 2 speakers, and then you can ask a physicist by sending in your questions on the chat. This is being held nominally from Arizona, but through the miracle of Zoom, we're all actually all over the world. Our first speaker, as you can see, is hiding in a closet in Australia, and it's Paul Davies, who is actually the director of the Beyond Center for Fundamental Concepts in Science at Arizona State University and a Regents Professor. He is internationally known for his fantastic work on quantum gravity, quantum fields and curved space-time in particular, but he works in absolutely anything that he finds interesting, from extraterrestrial life to cancer. So without further ado, I'm going to have him, invite him to give a presentation on today's topic. Take it away.
Well, thank you very much, Maulik, and hello, everybody. Thank you for joining us for this increasingly popular series, Ask a Physicist. Why am I hiding in a closet? Well, you could admire my lovely shoes here, perhaps, in the background. The reason I'm here is because it's summertime in Australia. It's a sweltering hot day, and it's also the national holiday. And so outside, there's a very large number of noisy young people playing music and likely to be very distracting. So I've retreated to this quieter location. So that's the reason for that. Now, when I was a student, which was actually in a previous millennium, I was a firm believer that life existed around the universe, and people thought I was a crackpot. In those days, it was fashionable to suppose that life on Earth is unique and it wouldn't happen again, and looking for life beyond Earth was tantamount to looking for fairies. Everybody thought it was a ridiculous idea. I want to share the screen, just bear with me a second so I can show you an interesting picture here. Let's see, here we go. There we go. And so this is me as a young postdoc, you see, and this was before the age of color photography, you see. In the front row, you'll notice there's a very young-looking Stephen Hawking next to a young-looking Martin Rees, now the Astronomer Royal, and that's Fred Hoyle in the foreground. And I'm only showing all this to emphasize that this handsome fellow at the back is in fact me. Why am I at the back? Well, probably because I was the only person there who took seriously the possibility of life beyond Earth. So I was sort of ostracized. Anyway, At the time, that's 1970, the view about life beyond Earth was summarized very well by Jacques Monod, Nobel Prize winner, French Nobel Prize winner, said somewhat sexistly, man at last knows that he is alone in the unfeeling immensity of the universe, out of which he emerged only by chance. Now, I have to say that this pronouncement coincided with a period of Gallic nihilism in which it was fashionable to celebrate the hopelessness and pointlessness of existence, and he looks suitably awful. But his view on the nature of life coincided with that of Francis Crick, by every account a much more jolly sort of fellow, no Gallic nihilism there, but he believed that life seemed almost a miracle, so many were the conditions necessary for it to get going. And so the upshot was, well, life is restricted to Earth. We wouldn't find it anywhere else. It was a bizarre fluke. Then fast forward to the mid-90s, and another Nobel Prize winner, Christian de Duve, took a very different point of view. The universe is pregnant with life, he said, that life is almost bound to arise wherever conditions are similar to Earth. And he had this wonderful phrase, life is a cosmic imperative. In other words, given an Earth-like planet and given long enough, life will out. And that's the view today. So it seems that what has happened in the intervening decades is that the fashion has swung from that we are alone in the universe to there are vast numbers of planets with life and some probably with intelligent life. It's very curious, that change of point of view. During that time, I should say, my own personal pendulum has swung the other way. I've gone from being very credulous about life elsewhere to being very skeptical, but that's a personal matter. Now, the great man himself, Charles Darwin, refused to be drawn on the subject of life's origin. Mere rubbish, he said, thinking about the origin of life, might as well think about the origin of matter. Well, I'm pleased to say that we physicists have now solved the problem of the origin of matter, but we still don't know how life began. And part of the reason is that the pathway from a mishmash of chemicals to a truly living thing, an autonomous entity, seems so enormous that and so many steps that we really don't know how to fill in the gaps. Now, it could have been easy, it could have been hard, but as we don't know what it is, you can't put a probability to it. And can't stress this enough. If you don't know the process that you're talking about, you can't say how likely it was. So it's completely open as to whether life on Earth began with a bizarre fluke, a dream run of chemical reactions that just happened to cook up life in a few million years, or whether there is a sort of deep life principle pervading the universe that fast tracks matter to life wherever the conditions permit. Could be anywhere on that spectrum. So I'd like to go with the optimistic view, although I'm a skeptic. The optimistic view is a cosmic imperative or a life principle. How can we go about testing that? Well, what we need to do, of course, is look for a second genesis of life, life 2.0, if you like, because if we only have one sample of life, it's impossible to tell. It's incredibly complex, of course. It's impossible to tell whether it was a fluke, a chemical accident of extreme improbability, or whether it was the inevitable product of some life-friendly underlying laws, which we have yet to discern. We don't know. So the obvious thing seems to be, well, let's go look for life 2.0. How do we do that? How do we find this second sample of life? Well, one of these is, of course, SETI. This is a well-trodden path. It's to sweep the skies with radio telescopes and other ways of looking for techno-signatures. And if we find there are civilizations out there, then it seems unlikely you get a civilization without passing through life on the way. And so the question will be answered. It will take one message from ET and this cosmic imperative will be established. But whilst we wait for that, we could look into other planets outside of the solar system, exoplanets. We could look for biosignatures in the atmospheres of exoplanets. Sara's got some ideas about that. I won't say any more, but this isn't something that's likely to succeed like next year or even next decade. It's actually really, really hard thing to do. And so again, whilst we wait for that, what else might we do? Well, we could maybe look for life on other planets within the solar system. Mars seems to be everybody's favorite, but the problem about the solar system generally, and Mars in particular, is this. It's summed up in this picture, that Mars and Earth take a hit, well, all the planets take a hit from time to time by comets and asteroids with enough force to splatter rocks around the solar system. And so Mars is continually being bombarded and flinging rocks to Earth. Those who are interested could check out the meteorite collection at ASU. There are about half a dozen Mars meteorites there. These are rocks that have come from Mars. I won't get into how we know that, but we do. And likewise, rocks will go from Earth to Mars. And so it's very clear the planets are not quarantined, to use a fashionable term from these COVID days. They're not quarantined from each other. You get life on one, you get it on the other. We could spend a lot of money and go to Mars, only to find, yes, indeed there is life there, but it's boring old Earth life, just got splashed there by an impact. What we really want is a second genesis. We want to find a place where life started, independently of Earth. Life on Earth started more than once. Just a single example of a microbe of life, but not as we know it, would suffice to make the case. Well, what's the most Earth-like planet we know? So the cosmic imperative said, wherever you have Earth-like planets, you have life, more or less. What's the most Earth-like planet we know? Well, it is, of course, Earth itself. So if it's true that life pops up readily at Earth-like conditions, surely it should have happened many times over right here on our home planet. How do we know it didn't? Has anybody actually looked? And when I got interested in this question about 20 years ago, I was astonished to learn that really nobody had given this much thought. They'd given a huge amount of thought to how Earth-like Mars might be and so forth, but nobody was prepared to draw the obvious conclusion that if life does form that easily, it should have formed many times on Earth. And then you immediately come on to say, well, might it have formed many times on Earth? And is it possible that descendants of a second or subsequent genesis here on Earth might still be all around us today? And so that's the idea of looking not just for another branch on the known tree of life, but another whole tree. Now, obviously, we would notice if something the size of an elephant or an oak tree were life, but not as we know it. But most life on Earth is microbial. The vast majority of species are microbes. And you can't tell by looking what makes a microbe tick. You can't tell. You look through a microscope, they're all little blobs. You can't say that's one of ours and that's a weird one. You've got to delve into their innards to establish if some of these microbes might be an alternative form of life. It could be intermingled and all around us at this time, and we might never know. We might never realize it. And part of the reason for that is that, as microbiologists will tell you, they customize their procedures for life that we know. They go out looking in the environment, how amazing, we found life here, we found life there. You know, how have they found it? They found it by going looking for signs of what they already know. They wouldn't find something that we don't know. It's a different biochemistry, even a different genetic code, wouldn't show up. So we could be surrounded by this second sample of life. And of course, that would make the point. You just need one microbe here on Earth. It's a lot cheaper to have a mission to planet Earth than to Mars, right here on Earth. And then if you've got two forms of life here, surely the universe is indeed teeming with it. So that's the basic idea. Could be aliens right under our noses, or even as one wit marked, in our noses. And this often goes by the name of the shadow biosphere. That was a term coined by Carol Cleland. And the idea of the possibility of a shadow biosphere has been sort of around on and off for about 20 years, but nobody's really done anything about it. There's been very few serious searches to see if we can find a shadow biosphere. Part of the problem, I should say, and I'm keeping one eye on the clock here, yes, but part of the problem is that if it is intermingled with life as we know it, it's very hard to separate it out. Much more easy would be if this other form of life could thrive in conditions beyond the reach of Earth life. For example, Earth life can exist under a very wide range of temperatures from like -40 to plus 120 or something, 125. But supposing you found no life between, say, in a deep ocean volcanic trench, no life between 125 and 150, and then a cluster of microbes that could survive between 150 and 180, then surely that would be something to concentrate on, a possible sign of an alternative form of life. So that's the sort of reasoning. But if it's comfortable only in the same condition as known life is comfortable, very, very hard to separate out. The only unambiguous case is that all life that we know, and Sara's like the world expert on this, is based on left-handed amino acids and right-handed sugars. That's called the chirality problem. It's all the same. And if you found life with it round the other way, well, then that would be a good sign for, that is mirror life, good sign for an independent origin. But we haven't found that, but we haven't really looked with any seriousness. So how might this work out in practice? Well, I mentioned this cosmic bombardment was much more severe in the past. And we can imagine that, say, 4 billion years ago, Earth settled down after this bombardment, life emerged, and we've got these microbes covering the planet. And then wham, along came a huge asteroid, maybe 300 kilometers across or something, that would have sterilized the surface of the planet with its heat, boiled the oceans and all these horror scenarios, and then flung a lot of material into solar orbit. And then after maybe 1 million years, everything would have settled down again. Life would have got going a second time. But then back came some of this stuff that had been orbiting the sun. And so you would then have two forms of life on Earth. You'd have the original and coming back, and then a new form. And this could have happened many, many times before things settled down. So that's a possible scenario. There are others. I'm not going to speak anymore. I'm just going to put up the conclusion slide. Why do we care about this? Well, if Earth does have a shadow biosphere, or even if it did have and it's gone, it shows that life will indeed be widespread in the universe. We don't have to go anywhere else to establish that. We can get that information from right here on Earth. And if that's the case, then life is obviously, as it were, written in to the laws of the universe in a fundamental way. I would say that the universe would be rigged in favor of life. And some people who, like Jacques Manonobel, I think, extol the idea that humans are just a sort of an annoying freak extra in the universe and not an integral and fundamental part of the unfolding of things. That point of view, I think, would be refuted by discovering this. And so there's a lot of philosophical as well as scientific issues that are riding on the discovery of this. So that's all I have. I'm going to be quiet now, and we'll deal with questions after Sara has spoken. So Maulik, I think you'd better take back control.
Yes.
Stop chat.
Thank you, Paul, for that. Our next speaker, and we'll have all the questions afterwards. But our next speaker is Sara Walker, Professor Sara Walker, and she is the Deputy Director of the Beyond Center for Fundamental Concepts in Science at ASU. And she's a biophysicist, and her area is, she particularly works on things like life and thermodynamics and all these things that go well together with a drink. So today she's going to claim that life happened only once. So take it away.
Thanks, Maulik. And thanks, Paul, for the provocative introduction to all the ideas to discuss today. So I'm going to kind of argue the opposite side of things from Paul, even though we actually might agree on some of the issues or disagree on other ones. But I want to convince you today that, at least as far as we know, life happened once, and there's no reason to speculate that there were even multiple origins of life on Earth, and that this idea of a shadow biosphere might be a bit misguided because it's not thinking about life the right way, in part because we don't know how to think about life because we don't know what life is. So just to start off, I wanted to give a couple quotes from some people I really respect on some of these issues, which is the fact that when we think about life, we're usually thinking about individual organisms such as ourselves, but maybe that's not the right way to actually ask these questions about whether life has emerged on Earth multiple times or what life might be like elsewhere. And so just to give you some insight into that question, David Grinspoon, who's thought a lot about planetary scale impacts of life, in particular in the Anthropocene, so the effects of human mediated climate change and what we're doing to the planet now, suggests that life is not what happens on a planet, it happens to a planet. So it's not a process that's just existing apart from the planet, it's actually intimately tied to the planetary context. And Everett Schock, who's a professor right here at ASU, has for a long time been making very strong arguments that biochemistry is what it is because that's what the Earth allows. So you can't talk about biochemistry without talking about the geochemical roots from which biochemistry emerges. We can contrast this with how other people talk about life, which is kind of the more traditional view. And Maulik mentioned this idea of thermodynamic views of life. And so this quote here is actually from Irwin Schrodinger, who was a major early proponent about thinking about life from a physics perspective, and wrote a very famous book called What is Life, which was asking exactly this question. And he came up with the concept of negentropy to basically describe how life is creating order from disorder, so doing the opposite of what we expect entropy to do in a physical system. But I think the way that he actually framed the question was entirely wrong for the kind of issues that we want to be talking about, especially within the context of thinking about life as a planetary scale process. So what do I mean by that? Well, in the beginning of the book, he asks a very poignant and very specific question about life, which is how can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? So he's asking about life within the boundary of an individual organism and thinking that is the fundamental unit that we should be thinking about living processes, and that's what life is. We can contrast this with the quotes that I just gave, thinking about life as a planetary scale phenomena. And we can then ask the question, what is life, but what is it at a planetary scale? And is that maybe a better way of thinking about it for this issue about whether life happened more than once? And so I'm going to talk in a minute about how we can think about that in some more abstract ways, but just to convince you that life doesn't just exist at the level of individuals, it's clear that individual organisms might be representative of this thing we call life. But we can also think of community scale things like ecosystems as being living processes. And if we scale that up to the planet as a whole, there are living processes that happen at a planetary scale. And so one of those that we talk about is actually what we call the biosphere, which is the global activity of all life on Earth. You might also think of a parallel, which is like the noosphere, or the activity of all intelligent life on Earth. And we clearly have global systems that we recognize very readily, such as the internet, that are globally integrated systems. And life itself is probably also a globally integrated system that's actually tied to the planet. What evidence is there for that? Well, in my own work, we talk a lot about this idea of thinking about biochemistry at a planetary scale. And so what I mean by that is if you actually look at all of the reactions that biochemistry mediates on Earth, you can study them at the level of individual organisms, ecosystems, or even at the planetary scale, and they have very regular behavior across all of those scales. And you can quantify that behavior and actually talk about laws of biochemistry in the form of what we call scaling laws, which are ones that apply across different scales that actually exhibit similar behavior. And so if you want to think about this from the perspective of networks, which are a little bit abstract, but easy to grasp for anybody that's on Twitter or Facebook, a network is just a representation of how components in a system are connected. So if you're on a social network and you're friends with people, you could be represented like a dot in one of these diagrams, as I have shown here, as a node, and you would be connected to anybody that you like or are friends with in your social network. And you can imagine the case where a social network might lose a whole contingent of people that have a different belief system to another social network, as we're bifurcating our social systems right now. And those are not very integrated systems. They're not sustainable systems. And so part of the argument here is that we're thinking about the network properties of life on a global scale. Having really radically different networks coexist actually isn't sustainable in the long term. And so for all of us that are social media savvy right now and seeing the things that are in dynamics that are happening on the internet, probably are pretty aware that, you know, non-integrated networks are not really stable. So another argument in favor of this sort of planetary view of life is that we know that metabolic networks, so the processes of the chemistry that happen inside of our cells, which is just the reaction that we can think about. So if maybe some of us just ate dinner, we're metabolizing right now. All of those metabolic processes have co-evolved with Earth's geochemistry. So they're not decoupled from planetary context. We're actually tightly coupled to planetary context. And probably the most obvious case of that is the rise of oxygen after the Great Oxidation Event. So photosynthesis was a metabolic process that evolved and started producing abundant atmospheric oxygen, which ended up actually poisoning most species on Earth. But then the ones that survived actually became dependent on oxygen, some of them, and other ones moved to environments where oxygen wasn't readily available to poison them. But that whole process actually changed the entire Earth system as a whole, and life had to co-evolve with it. So it's not that life on Earth is actually independent of its planetary context, it's actually tightly coupled to it. And even if we think about the origin of life itself, there's a lot of evidence that ancient metabolic networks, so the first metabolic or chemical processes that emerged on planet Earth were actually a process that came from geochemistry. So we shouldn't think of the origin of life as this spontaneous fluke event. You know, at last, as Paul was saying, at last we know we're alone in the universe. It's such a rare occurrence. But that it actually is a process that emerged from the planetary geochemistry that was happening at that time on Earth. And therefore, the chemistry that evolved into life is actually a product of Earth. And it's actually very coupled to the Earth system. So to think that other examples of life that are completely detached from Earth's geochemistry would have emerged is making a radical leap and suggesting that life is more of a rare fluke, which then suggests it should be less probable for it to actually be coexisting, a second sample on our Earth. Just to take this one step further, if we can think about these biochemical networks that we have on Earth, we can try to think about thought experiments, transplanting them to other worlds. And this is actually a thought experiment that one of my former students, Harrison Smith, did during his PhD work, where he thought about trying to take all of biochemistry on Earth and moving it to another planet, or actually in this case, a moon, and on Enceladus, and saying, given the molecules that we know on Enceladus, how much of the biosphere could we reproduce there? So the idea here is we have geospheres, like we have on Earth. We have the geosphere, which the biosphere, which is all life on Earth, is tightly coupled to. If we could remove the biosphere and actually couple it to another geosphere, that would be suggestive that maybe life can be moved between planets, or maybe life isn't as tightly coupled to planetary context as we think it is. But the evidence that we got is actually, well, you really need to take the whole biosphere if you're going to do that, because the biosphere reproduces a lot of things it needs, and Enceladus doesn't have all the ingredients actually for the biosphere on Earth to reproduce itself, at least as far as we can tell from the evidence that we have from mission data so far. So transplanting a biosphere is very hard. Imagining that two biospheres that are radically different could emerge from the same planetary geochemistry is also very difficult to envision. So probably you get one example of life per planet, and that example of life, at least at the chemical level, is very contingent on the planetary geochemistry. However, I just want to introduce one idea at the end, which is this idea about multiple origins of life proposed recently by some colleagues at the Santa Fe Institute, which kind of resonates with my thinking about life, proposed by David Krakauer, who's the president of SFI, and my colleague Chris Kempes, who works on a lot of scaling stuff with us. And their idea was basically that the origin of life on Earth has happened multiple times, but it doesn't happen in chemistry every time. It's just that a lot of things, every time we see sort of a new emergent information processing system, like culture or technology or multicellularity, those are actually separate examples of the origin of life happening again and again at different scales. So this again gets at the idea that when we're talking about thinking about life at the scale of an individual and trying to define it in terms of its chemistry, then maybe we have flawed ideas about what life is, and therefore we don't have the right framework for talking about how many times life on Earth has emerged. So I'm going to argue that at least chemically, life on Earth has emerged only once. And because it's a globally integrated system, a little bit like our internet or social networks are aimed to be, we can only have one example of it per planet. It's integrated with the planetary geochemistry. But maybe if we have this broader view of life, the origins of the process that gave rise to life might have happened in different systems that are very different media than just chemistry. And I'm going to close there. Thanks.
Okay, thank you for that, Sarah. So now we're going to turn it over to the audience, and if you have any questions, then please just enter them into the chat. You can address them to everybody, or to me, or to the speakers. Well, preferably to me, actually, or to everyone, because I'll be moderating it. Our first question comes from Barbara Temple, and the question is, when do we consider life to have actually begun? Is it when DNA or RNA have been created, or when self-replicating proteins have been created? Do the genetic and physical aspects of life coming into being qualify for life occurring twice? So, well, I think maybe I will pass that question on to Paul.
Many years ago, I attended a lecture at the Royal Institution by George Porter on the origin of life. And he started out by saying that there are lots of debates about when does life begin, but in his view, it's when the children have left home and you've got rid of the dog. so there are, of course, decades of discussion about what it is that constitutes life. Sara and I have collaborated, and she'll probably say a few words about this, on trying to define life not so much in terms of the chemical hardware, was it DNA, RNA, or something like that, but in terms of the informational architecture, if you like, the software of life is what marks the true beginning. It's certainly, in my view, that's what I feel is the key thing, not just complex chemistry. So it would be very, very hard, I think, to point at some step on this pathway and say, there it is. And Sarah's been arguing for a planetary scale. Maybe if that was something like a phase transition on a planet, you could then mark it to be that. But I think in practice, it would be very hard. Sara, do you want to pick up where I left off?
Yeah, I mean, I think one of the things that really struck me about this sort of informational definition of life is I think you'll know once you have life having had emerged, but you won't know when you cross the boundary. So that problem of, you know, the exact point that you cross the boundary between non-life and life is actually not a well-defined transition. But I think just to build on what Paul was saying, we do, you know, sort of the more traditional answer you might get for this kind of question is that we do have fossil evidence for life on Earth that dates back between 3.5 and 3.8 billion years ago, depending on who you ask. And so there's evidence in the fossil record of life emerging very early. But as far as the first living things, when you think about that sort of DNA-based, protein-based organism, that's a very evolved system. And so that's not often what we think about when we think about what the first living thing was. And in fact, we don't know how to break down the way we think about the organization of life in modern cells and take those properties back in time to really understand what those first steps were, which is one of the reasons that Paul and I have adapted this kind of more abstract view based on more fundamental principles, because it allows you to talk more generically about the processes involved in life and allows you to look at simpler chemical systems and evaluate how alive they are. But, you know, that's still very much a work in progress.
Could I just have an addendum, just pay tribute to my friends here in Australia who have worked over the decades on the oldest agreed traces of life on Earth in the Pilbara region of Western Australia. It's a wonderful place to visit if ever we're allowed to do so again. And that dates back nearly 3.5 billion years. And Martin van Kranendonk from the Australian Centre for Astrobiology thinks he has evidence for life in rocks from Greenland 3.8 billion years ago, but that's more controversial. So it's really going back a significant fraction of the age of the universe. But in terms of what defines it as living, you know, these are geological traces. There's no organic material of any substance that can be used to say, yes, that was life. This looks like life.
So on the subject of fossil evidence for life, here's another question. This one is from Derek Youngson, and I think I'll pass it to you, Sara. It says, are we able to look for extinct life on exoplanets based on their age, their likeness to Earth, the spectral signals, or whatever?
Yeah, I think we'll be very lucky if we can find living life on exoplanets, let alone extinct life. The places where I think you might have the best chance of finding extinct life forms on an exoplanet is actually if they were technological life forms and they formed some kind of pollution that lasted longer than the age of the civilization did. But most biosphere, most biosignature candidates for exoplanets require an active process on the surface to drive some kind of disequilibria condition in the atmosphere. And so you would expect to only be able to detect them remotely if life is active on the surface of the planet or over a finite time window after the death of that biosphere. So in general, when we're talking about exoplanet searches for life, we're not looking for extinct life because that's too hard to detect. It's hard enough to actually look for biological activity itself.
Okay, and on a similar note, Phil T, our friend Phil T asks, why did you choose Enceladus? What is special about that moon? So,
Well, there's two real motivations. One is that it's been a target for upcoming NASA missions for life detection. So there's been a lot of interest in it because Enceladus has an active plume that's basically jetting out organics into space. And so people want to fly through the plume and try to sample and see if we can detect life there. But the other reason is that it had more data about the kind of molecules that might be present on Enceladus because of the presence of that plume than we had for other icy worlds, like for example, Europa, which is another target you might consider. So it's a combination of the fact that it's an active target for life detection and the fact that we have more data.
okay. And here comes the inevitable question about Venus, which has been so exciting. This is from Mike Mout, who asks, what about the recent evidence from Venus indicating some sort of life that generated a chemical signature, the one that maybe you'd like to describe what that signature is as well? And
I have a lot to say about that one, actually. So the molecule they detected is called phosphine, and it's a potential candidate biosignature because of the fact that it may be produced by life on Earth, although the exact mechanism of producing phosphine in biochemistry on Earth isn't known. So the discovery of phosphine in the Venusian atmosphere was heralded by some as a confirmation that there might possibly be life in the atmosphere of Venus because there was no known abiotic explanation, and because on Earth there is a possible biological explanation. However, I think if you kind of think through the logic of that kind of approach to biosignature science, it reveals a lot of flaws in the way that we're currently approaching the problem. A lot of the ways that we talk about life detection on other worlds have to do with the fact that we can't find an abiotic explanation. So we don't have an actual explanation. It just means it's an anomaly. There's no explanation for it. And that it might be explained by a biological process that could happen on Earth. So we're always doing it by analogy to what happens on Earth, and by virtue of the fact that we don't have a better explanation for the data. And so that's not actually testing any hypotheses about what life is or thinking very rigorously about how we can take processes that happen on Earth and transplant them to the environments of other worlds and actually really understand how they would operate there, because we don't know enough to do that yet. So I think a lot of people in the community kind of agree that the phosphine story is interesting because in a planetary science context, but that we should not take it very seriously yet as evidence of life. It's very far from being evidence for a biological process.
And also, Sarah, would you agree that the problem of cross-contamination that is going to occur because Venus and Earth are not quarantined, Earth rocks will certainly have gone to Venus, and there may be life in the clouds of Venus, but it's just boring old Earth life, just transplanted there.
Yeah, I think that's possible. I haven't really focused on the issue though, because I just think the standards in the astrobiology community for when we claim possible detection of life are just so low. And it's just really like, we need to really think more rigorously about the problem and build better standards as a community before we make announcements about those kind of discoveries. But that's my personal bias, because I just want astrobiologists to actually be able to move to being able to say confidently we detected life, and that's going to require us to challenge ourselves in ways that we're not doing now.
Don't cry wolf too often.
Yep. Yeah.
okay, here's a fascinating question from Juliana Churston. This is a very physicsy approach, so I like it. It says, both life itself, as well as manufactured artifacts produced by hypothetical ancient intelligent life, are unique in that they are highly ordered. right? So they have low entropy is the technical term. Can we build generically an entropy sensor that, regardless of the material of a sample, can reveal how ordered a sample is and use this entropy measurement as a proxy for how likely it is to have been made by intelligence? So, Paul?
Yes. Well, that's the big question. It's a very fundamental one. Sometimes Sarah and I talk about building a life meter, which would be the same sort of thing. So is there something about the organization or the information that would suggest that it's living? It's actually philosophically a really, really difficult problem. And if I just give the example, I think we dealt with this in a previous Ask a Physicist, looking for a techno signature, as we call it. So what would be a signature of alien technology? Certainly, if you look at my computer screen now, product of human technology, it's very highly ordered compared to thermodynamic equilibrium. And so that's a good example of it. But how could we generalize that to technology that we don't know? The product of some other civilization or cognitive architecture? Is there some sort of objective definition of when something looks artificial or designed as opposed to natural? We don't have such a thing. I could talk a great length about it. I'm going to stop here because there is so much I could say about it. It's a very pertinent question, in my view, unsolved.
Great. Thomas Hullon asks a philosophical question. How many answers are there to the question, what is life? And how would you characterize the different approaches? So I don't know who wants to take that.
Well, I think there are a lot of answers, but I put in another plug for the upcoming Beyond annual lecture by Paul Nurse, Nobel Prize winner, former president of the Royal Society in London, now director of the Crick Institute, whose book, What is Life, follows on from Schrodinger's, and he's probably going to have a great deal to say on that particular topic. I've got a great deal to say as well, but there isn't enough time left. And so Sarah might want to say something.
I just want to say something quick, which is I would say there's probably as many definitions for life as there are people that have thought about it, because I think, it's just a really hard problem. But I think one of the issues is that most of the time when we're trying to approach the problem of solving life, we're worried about describing life as we know it, rather than trying to think about what is the fundamental missing piece of how we understand the world that we could derive the properties of life from. And I think those approaches are really different. And the reason that I favor the latter is because I've been trained in physics, and I think there's some, first principles approach to understanding the universe that will allow us to understand why life exists in the universe and what it is. But most of the time when we come into that problem, we're just trying to start at life, assume it exists, and then define its properties, not try to derive life from some other more fundamental aspects. And so I'm hoping that maybe that might be more fruitful. We'll see.
Okay, here's a question from Justus Bergiolas. I hope I'm pronouncing that correctly. It's a provocative one. Could advanced civilizations have existed on Earth before humans? Though we have not found any evidence.
That's a question.
Yeah. There's a famous speculation by Chris McKay that the dinosaurs, of course, ruled the Earth for 200 million years. How smart were they? Well, it turns out there's a particular species of dinosaur with an encephalization quotient that is sort of like brain mass to body mass compared to the norm. That was 5 million years before the end of the dinosaurs, had a bigger encephalization quotient than our own ancestors 5 million years ago. So how do we know that the dinosaurs didn't form a civilization, make rockets and go to the moon? Well, it would be interesting if we explored the moon and found dead dinosaurs there. As far as I know, that hasn't happened. I think we'd all know about it. But that's a sort of interesting question. Rather more plausible, in my view, is that given what we're uncovering about human history, and I'm talking not just about Homo sapiens, but the other species of Homo, like the Denisovans and the Neanderthals and so on, it's a much richer history than we thought. And you have to wonder whether something approaching technological society might have happened on Earth, say 2 million years ago, something like that. Is that possible? Homo erectus created a civilization in Southeast Asia, and it's all under the sea now. If it was localized geographically, it could be submerged, and we would have no way of knowing that had happened. So it's a fascinating speculation. I read a paper about it recently. I was scrambling to find it on my computer. I haven't done so yet, but can send it a copy of it to the questioner. I have to say, I think it's extremely unlikely, but it does force you to think about how would we know and what are the enduring aspects of civilization. Because if humans were wiped out tomorrow, how much of our stuff would still be around in a million years? And the answer turns out to be not very much.
Okay, here's a question from Steve Ruff. This is one on referring to the discovery a few years ago where they found microbes that were based on, not on carbon, but on arsenic. And so the question is, are those arsenic-based microbes fully dismissed as second genesis on Earth, or is this still a possibility?
Yeah, I'll take that because I was a bit involved in that, and there was never a claim this was a second genesis. It's something that the media got a hold of. There's no doubt that there are microbes that survive in huge amounts of arsenic under the conditions of rust would be very unpleasant. And there's a paper in Nature just last month on some new work that was done on this. But this is not anything like a second genesis. The work that was reported a few years ago was of a microorganism that sat firmly on the known tree of life, but just was handling its arsenic in a very peculiar way, which became a very controversial topic. And we may not have had the last of that.
Okay, so now looking again outwards, Thomas Ruth asks, is consideration made for life on dwarf planets, moons, asteroids, etc., or do we only consider possible life on defined planets? So I think, well, Sara, I'll let you take that.
Yeah, no, I mean, so especially in the solar system, some of the moons are actually prime targets for life detection. So I mentioned Enceladus and Europa before, but also Titan is a moon of Saturn, which is a target for life detection. So we certainly do have some ideas that life can exist on moons and not just planets. But I think it depends on some of your assumptions about how deeply embedded like living processes are with planetary processes, and maybe there's a certain mass scale or a certain diversity of chemistry or things that can only happen on planets of a certain size. I'm not really sure on that, I'm just speculating, but at least as far as sort of the party line is, most astrobiologists are equally happy to look on moons or dwarf planets as they are on planets, as long as the conditions are quote unquote habitable, i.e. there's water, some kind of liquid and other properties.
And a related question by Nicholas Rudolph is there a list of probable locations in the solar system that we've ordered in priority for study? It's kind of short list for where we might look.
There's a list. I don't think there's any consensus priority. You can ask any of our colleagues that work on missions to these different targets. I mean, I think they're all respectful of other targets, but people have their favorites. So among those are Venus, we discussed, and Mars, and Enceladus, and Europa, and Titan. And those seem to be the primary targets for astrobiology for very different reasons for the different worlds or moons.
I should just say that I started out with an ancient picture from Cambridge University with Fred Hoyle sitting in the front row. And he was famous or infamous for suggesting that maybe life is cooked up in comets and delivered ready-made to Earth, because of course comets are always sweeping past and cometary dust comes down. And this was regarded as utterly beyond the pale at the time. But in hindsight, it's not so dark, actually. It's not impossible that the conditions inside comets are as good as anywhere to incubate life. And if you had life in comets, whether it started there or got scooped up from planetary debris in the way that I described earlier, either way, it would probably get propagated around. So his ideas, and it could, by the way, it could also be the case that planetary systems fling out these comets and then they travel across the galaxy and then come to rest inside planet-forming giant molecular clouds, planet and star forming, and seed them with life. I think all of this is a bit of a stretch, but it's not nearly as crazy as people thought when Fred suggested that back in the 1970s.
Here's a question that, well, we know that on Earth, life formed relatively quickly after the formation of the Earth. And so Gerard Milburn asks whether that time, the time taken for the chemistries of a given planet to produce simple life forms, would be different on cold planets versus on hotter planets.
Well, because if we knew what the chemical pathway was, we could then work out the rate constants and so on. I thought that Gerard was going to ask the fact that it started so quickly on Earth suggests that it does start up pretty readily in Earth-like conditions, and the rapid start is consistent with it being easy to make. But as Brandon Carter showed many years ago, it's also consistent with it being very hard to make for the simple and quirky reason that if it hadn't got going quickly, we wouldn't be here now to discuss it before Earth became uninhabitable. We've got about another 800 million years and then it'll get too hot for life here. So there's a window in which life can appear and evolve, and for beings like ourselves to reflect on their existence. And so it could be either way. It could be it's very easy to get going. It's very hard to get going. And this is what sometimes goes under the name of the Entropy principle or the doomsday argument. Number of different twists on that fascinating topic. I can't remember if we did an Ask a Physicist on that, but if not, we should put it down on the list.
That's a good one.
Here's a question from Rios, who paraphrases Enrico Fermi and laments, "Where are they? What are they doing? Why are they silent?"
Yeah, well, of course, there's a book called 51 Solutions to the Fermi Paradox. So plenty of reasons why ET could be out there and not here, or here and we don't notice. And if we're talking about intelligent life, that is so. If we're talking about just life, then I tried to make the case it could well be here. It could be all around us. All you've got to do is look. Could be right in your lab now. And the difficulty is actually identifying it or getting funding to be able to work on something.
Yeah,
So
we need funding for more clever solutions. I'm just going to second that last point because I think we just don't know what we're looking for.
And unfortunately, microbiologists, if you're doing your PhD studying some particular interesting microorganism and you try to culture it and you try to sequence it, and if none of this works, you throw it away and you go and work on something else. You don't say, oh, maybe this is an alternative form of life. You won't get your PhD that way. And so the whole system is, I'm afraid, rigged in favor of not finding life 2.0 right here on Earth.
So Kevin Smothers is saddened by the destruction of Arecibo. You remember that there's a legendary radio telescope that recently was destroyed. It was actually on the verge of collapse in Puerto Rico, and asks whether the search for extraterrestrial life has been impacted by that, and are there plans for another dish? Anybody know?
No, it hasn't, because that hasn't been used for quite some time. The current funding is for the Green Bank Radio Telescope in West Virginia and the Parkes Radio Telescope in New South Wales in Australia are the principal instruments. There's also the Allen Telescope at Ray and Hut Creek in California that is being used for that purpose. And people talk about the Square Kilometre Array, which is in the process of being constructed in South Africa and Australia, might have a SETI mission as well. It all comes back to the funding as ever.
Okay. Well, here's another question. Are astronauts still quarantined for alien organisms when they return?
I'm probably the only one here who remembers the first Apollo mission with the astronauts. I mean, talk about ridiculous. They sort of stepped out of the spacecraft and waved at everybody and then went into a funny little caravan and then waved out the window. If they were going to bring back space bugs, it would have, well, as we now know in these COVID days, that's no sort of quarantine. No, they gave up doing that. But there's a lively discussion about whether rocks being returned from Mars should be quarantined, and that's the current protocol. In fact, some people are so fanatical about the dangers of a killer plague from the red planet that they're talking about you do the sample return on a trajectory that won't actually hit the Earth until the last minute, and then you divert it so it comes, well, maybe to the International Space Station, and wait and see if the astronauts die first before bringing it back down to the ground. They're various sort of legal arguments back and forth, but it's going to be a while yet before this happens.
Okay, we're almost out of time here. I think maybe one or two last questions. Here's a question from an anonymous person. It says, viruses, of which we've heard all too much in the last year, are actually dominating the Earth in terms of amount. Is that true? We've found a large amount of them in ancient ice layers. Does that indicate possibility of having had life before?
I think all the viruses we know are worrisome because they're adapted to life as we know it. That's why they are so effective. Vast majority of viruses are not harmful. They form like mobile genetic elements, and taking Sarah's view of life as a planetary phenomenon, they're part of that network of information exchange. And I think without the virosphere, the biosphere as a whole would probably collapse. So I think viruses are generally good for you.
And just to add to that, I mean, a lot of people speculate viruses are about as old as life itself, and some scenarios for the origins of life actually propose viruses were critical at the very first stages of life. There's a really well-known book by Freeman Dyson called The Origins of Life, where he has his garbage bag hypothesis where there was some like autocatalytic systems forming and viruses formed alongside of them, and then the viruses infected the metabolism, and then that became life as we know it. So I think if you think about the history of viruses, they're certainly at least as old as cellular machinery is, as far as we have evidence for, although the exact ancestry isn't known that far back, but there are hypotheses that they're as old as life itself.
Okay, we're 1 more minute. I think I'll ask one last question. We've heard a lot about the birth of life, but here's a question from Prabhu Bharatan, who asks whether do all living things have all species sort of die also? Is there extinction inevitable? That's how I'm paraphrasing its question.
To be alive is to die eventually.
Well, some people work out the average duration of a species. It's actually not very long, 1 million years or something. And they say, well, that's all we're going to get.
Right.
But I think humans have sort of transcended the vagaries of Darwinian evolution.
Yeah, I think Nick Bostrom made a good point on this, that, with the invention of advanced technology and AI, it might be our best bet for becoming an immortal species, because otherwise we're going to face the fate of all other species that have ever lived unless our technology actually enables us to not die out as a species. So statistically, very likely, unless something radically different happens. And of course, technology and invention of artificial intelligence might just be such a radical shift.
And then plan B is we just spread out across the galaxy. So even if life, human life on Earth gets wiped out, the flame of our culture lives on somewhere else. But I'm very skeptical about that approach. And I think the AI one is much more plausible. We will live on through our designs.
All right, well, we're out of time for today. Those were lots of engaging questions. We're going to have another Ask a Physicist next month. Jessica, would you like to say anything? Otherwise, goodbye to everybody. All right.
Thanks.